to make a little video to go over some of the statistical process control methods, not as much about the theory, but more about how to do the math calculations. So we're going to start out by looking at just the general idea of what all this statistical process control stuff is and why does it matter. Seems to me that the best way to do that would be to talk about this chart here that has some of the common control limits that we see in statistical process control. We talked briefly about this in class, but just to have this as a reference is a good idea, I think. So you see here there's these control limits that we have that we're going to use commonly in this chapter. You see 90% is the z-value of 1.65. So that would mean if we want our confidence intervals set at 90%, assuming 90% of the processes without defects, we would use a z-value of 1.65. And 95% we see 1.96, and then 95.45% we see 2, etc. So I want to show you using a normal distribution what this exactly looks like. So what I tried to do here was draw a couple of the key z-values so you could get the idea. Now we've talked in class, regularly about the relationship between z-values and normal distributions and all those charts and stuff. So just to show you one more time, for many of you this may be redundant, notice z-value of 1 means we're talking about plus or minus 1 standard deviation on this normal distribution. It's going to include 68%. So on the chart on the previous page, of course I don't have 68% on here, but if I did, it would have a z-value of 1 and the control limit would be 68%. But on here, so we have z equal 1 here, because that's noting this line where the blue changes to red on both sides. I only have it written on one side, but you could see that it would be here and then right here. So maybe I'll write it on so you can see. Okay, so now you can see where I put it on here that z equal -1 here, so that includes all of this blue region, and z equal -2 here, which would include the blue and the red region on either side, and it would total the z-value of 2 would be 95.43% of this whole normal distribution. So that's how we come up with the z-values that we use in our X, R, P, and C charts. So we're going to move on now to P and C charts. We call these attribute charts, remember, because in C charts we call these attribute charts, and we do that because these events are attributes. They're not necessarily continuous events that we can put on a scale of 1 to 100. These are events that occur or they don't occur, or they're good or they're bad, or they're many errors or not very many errors. These are not continuous in nature. So we have to use a different type of chart. We can't use the same way we've always done it. So it just so happens that P and C charts have a binomial distribution versus a normal distribution, which just kind of means it's pushed over to one side like this, and that's really sufficient information that you need for this class. If you're interested in binomial distributions, let me know. I'm happy to talk to you about them. The control limits for P here are computed in the following way. The P bar, which is the mean or the fraction of units that's defective, or the percent of units that we're accounting for, and then this thing right here creates the standard deviation, or that little bit of variance on either side that we expect, and I'm using the term variance loosely. It's not actual statistical variance, but just the amount of, say, variation that we see on either side. Z, of course, is the number of standard deviations. This is the how to compute the standard deviations. And then N, I think some people got confused about this. N is the number of observations in the sample. And remember, there is the sample, and then there's the total number of observations. The total number of observations is going to be the sample size times the number of samples, and I'll show you that. I'm going to do an example here and you'll see what I'm talking about. So like I told you, P bar is the total number of errors divided by the total number of records examined. So in the example that we're going to work, we're going to have 20 different samples taken, and each of the samples will be comprised of 100 units. Thus we get 0.04 for our average number of sample defects. We expect 4%, or 4 out of 100 defective units. We compute the standard deviation of P bar in this manner. We take the P bar times 1 minus P bar and we divide it by the sample size, and so the sample size is 100. So I can't reiterate this enough. I had several people ask me after class, and other times they want to make this denominator 20 times 100, but no, it needs to be 100 because 100 is the sample size. So we're going to get 0.02 rounded up, of course, from 0.0196. So in this example, which is the same as the one we did in class, we're going to have 0.04 plus 3 times the standard deviation. So we have an upper control limit of 10, or 10 units defective out of 100, and the lower control limit of 0, because we can't have a negative percent defective. Had we actually calculated this out, of course we would have a negative number. So now I'm going to go to the handout and kind of walk you through the computations here. So first, we want to compute the proportion of defects, and so that is essentially P bar for us. And P bar is calculated as the sum of all of these errors divided by the sample size. And in this case, the sample size is 100 because we have 20 samples, and we have to multiply that by 20 because we have 20 samples. So we compute P bar as the total of the errors divided by the total sample multiplied by the sample size. So you can see here that I computed P bar, and I get the sum of the errors divided by the total number of samples times the sample size. And so that in this case is 80 divided by 20 times 100 is going to be this 0.04, or about 4% error, which translates to 4 errors out of 100 inspected. So now we need to move down to take a look at the standard error. So we want to compute the standard error for P bar. So we have P bar standard error, and we compute that as the square root of P bar times 1 minus P bar over N, when N is the sample size. And so in our problem, P bar is going to equal 0.04. Our sample size is 100, and well, that's just all about we need. So we can just then put those numbers right into our equation. So we're going to take the standard deviation of P will equal the square root of 0.04 times 1 minus P bar over 100. Made a mistake there. Let me change this. Not P bar. We're going to put our 0.04 there. And this should give us 0.019, or we're going to round it to 0.02. So this is the standard deviation of P bar. So I think I'll write that there. This. So now we'll go back and we'll put it in our handout. So we'll go ahead and put it right in here that the proportion of defects, of course we did that on the previous one, that's we call that P bar, is 0.04, and then down here what we just calculated, the standard deviation of P bar will equal 0.02. So now, what's the upper and lower control limit at 99.73% given our standard deviation calculation? So we know that this 99.73% means Z equals 3. So to compute the upper and lower control limits, we'll take the upper control limit will be P bar plus our Z value, 3, times the standard deviation of P bar. So we'll go right up here and where we have a little bit of space to calculate it. Upper control limit is going to be 0.04 plus 3 times 0.02. And then the lower control limit, the same setup, 0.04 minus 3 times 0.02. So you can see that the upper control limit then is 10% right here, and the lower control limit is actually -2%, which is wrong. So I wanted to show you that, and I wanted to then circle it and say no, 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 we don't want that. We are going to, if it's negative, we're going to change it to 0 because we cannot have negative number of defects. So given our question here, number 4, what's the what's the upper and lower control limits for this one here? We're going to have 10% or 10 out of 100 and 0. That's the upper and lower control limit. Let me just write down here, LCL is going to be P bar minus 3 times the standard deviation of P bar, and that is going to equal, I'm going to erase this so I have a little more space. It's going to equal 10 on the top and 0 on the bottom, 10% of defects and 0 on the bottom. Now this next part here, same idea, asks you to do it at 95%. So 95% we know from the previous slide we were looking at should be 1.96 for a Z value. So we're going to do the same thing. I'll calculate it up above. I'm going to erase this, and we'll change it. We'll change out the 3 to 1.96. Get rid of both of those things. It's a little easier. Plus and minus. It's going to be 1.96 and minus 1.96. And we'll get rid of these answers here. And then you can calculate it yourself, and I'll calculate it. So you can see up here I've calculated on the top, the upper control limit will be about 8%, and the lower control limit goes down below 0, so we'll just round it off to 0. So this is to be expected because we are bringing our limits in here on the normal distribution, instead of expecting a defect level to be 99.73. We are reducing it down to only 90% at a 95, only 95%. So we're going to allow our amount of defects to be higher. We're going from 1% essentially to 5%. So now we're going to change gears a little bit, and we're going to talk about C charts. With C charts, we're making the assumption that we've got a Poisson distribution, which allows us an even simpler calculation for the standard deviation of C. It's very much the same as the previous methods, but in this case we don't have a proportion of defects, we just have a number of defects. So in the example that we have that we're using in class, it's like the number of people that called upset, like irate phone calls from the cab company or something like that, because all we have is just an average number of defects. We don't have a percentage of defective units. Like with the P bar, there's a maximum number, but with the C bar, we don't really know. There could be an infinite number of possible problems. So the C bar chart, we add up all the number of possible defects, and then we just divide it by each day or the unit, and then we take the square root of that to get the standard deviation, and we can go ahead and calculate it very much like we did the P chart. So let's just turn our attention then to the handout, and we'll take it from there. So here we have the C chart, and with the C chart what we want to do is first calculate the total number of defective units divided by the total number, in this case, of visits. So we have this many errors, and I believe it turns out to be 45. So C bar will be 45 irate callers that called over 9 days, making C bar equal to 5. So right here in step 1, we'll put 5 here, which is C bar. Then if we calculate the standard deviation of C, we just take the square root of C bar. So the standard deviation of C bar is just going to be the square root of 5, or 2.236 right here. So now we know that on average we expect 5 irate callers per day with the standard deviation, or the amount of variation around that mean, of 2.236. So we'll put here the standard deviation of C bar will equal 2.236. The upper control limit then is going to be calculated as C bar plus, and we'll do it at 3 standard deviations, 3 times 2.236. Oh, excuse me, I should have wrote the C bar here, which is 5. And then the lower control limit of 5 minus 3 times 2.236. And we have an upper control limit then of 11.7 and a lower control limit of 1.7. Then it says, what are the upper and lower control limits if they are interested in having 90% be their control limits. So there we're going to need to modify our Z value from 3 down to 1.65 and recalculate. So I'm going to do that right up here. The upper control limit then will be 5 plus 1.65 times 2.236, and the lower control limit then will be 5 minus 1.65 times 2.236. So when you calculate that out, you get positive 8.69 for the upper control limit, and then for the lower control limit you get this negative 1.31, but of course we don't want any negative numbers, so we're going to cross that out and just take it to 0, because we cannot have negative amount of callers calling in irate, of course. So so then going back here to this question, it says what are the upper and lower control limits if they're interested in determining 90% of the defects? Well, then we have an upper control limit equal to 8.69, which we would just round up to about 9, because you can't have a part of a person, and we have a lower control limit than LCL equal to 0. So then the next question says, assume on day 10 she received 10 complaints, and on day 11 they received 7 complaints. What is the new upper and lower control limit with a 95% confidence? Okay, so now So in order to do this last problem here, we need to do a little bit of recalculating. First we need to recalculate C bar. So we're going to take 45. C bar will equal 45 plus 11 plus 7, which will equal 63. Then we have to divide now by not 9 but 11 observations. So we're going to get 5.72. Now we have to make a new standard deviation of C bar by taking the square root of 5.72, which would be about 2.39. Now we can calculate this problem down here. So the upper control limit will be 5.72 plus 1.96 times 2.39. And the lower control limit will be 5.72 minus 1.96 times 2.39. So we end up then with the new upper control limit of 10.4 and the lower control limit then of 0. So hopefully this provides a nice summary of how to do these attribute charts. And you're able to give it a little practice and get it in your head how to do it. I'm going to provide here on this next page just a summary of the homework problems that you ought to do to practice up for class on Monday. So just like it says on your handout, to practice these problems you want to do S6.2 and this S6.2 as well as S6.4. These are both X bar charts using the standard deviation. Remember, we calculated the standard deviation of X bar as a standard deviation over the square root of n. So that's what both of those are doing. 6.5, this one has you doing using the upper lower control limit with the factors. Remember, the upper control limit for X bar uses the A2 factor versus the upper control limit for the R bar will be using the D4 factor, and then the lower control limit the D3 factor. So that's 6.5. Then I have 6.11 on there, and 6.11 is also using the factors. And then I have 6.13 and 6.17. So 6.13, those are going to be, S13 is going to be a P bar. And then 21 and 23 are C bars. So there you go. I hope this is helpful. And have a great weekend.